We're going to start with Chapter 1, What is Science? Chapter 1, we're going to discuss the following topics: objects' properties, measurements, measurement systems, metric prefixes, fundamental properties, data, ratio, density, symbols and equations, the nature of science, the scientific method, hypothesis, experiment, law, model, theory, and pseudoscience. So to start off with, we're going to talk about objects. So objects are things that are part of our physical world, meaning they have to be able to be seen or touched. The three examples you see here: a chair, a rock, a tree. These are all examples of objects because they are things that can be seen or touched. There are things that are part of our world which are not considered to be part of the physical or natural world. An example would be your faith. That is still part of your world, but it cannot be seen or be touched, so it cannot qualify as an object. Now, all objects that meet this criteria have what we call properties, and these are qualities or attributes that are characteristic of the object. So, for example, this chair. Chairs can be made out of metal, they can be made out of plastic, they can be made out of wood, like it appears this chair is made out of. And chairs can be different colors. They could be red, blue, green. This one appears to be a brown wooden chair, and that makes this chair distinct from maybe another chair, which is made out of a different material and a different color and maybe even a different shape. This rock has kind of the same distinct features. It's jagged, has kind of a beige gray color to it. You can see here that there are maybe what appears to be some shells that were fossilized into this rock, which makes it unique. Here on the right hand side we have a tree. It's a tree that's kind of medium sized, has quite a lot of leaves, and kind of a short trunk that's brown. And so these are qualities or attributes that are characteristics of these three objects. Now, one of the things we use to describe qualities or attributes are what we call reference. And these are things that are comparative properties and other more familiar objects. So for example, when you look at the sky, it has a characteristic color that we might call sky blue. And if you were to say, I bought a rope recently that is sky blue, in your when you're trying to identify which rope they might be describing, you're going to find the one that looks like it's sky blue. Now, one of the problems with this is that the language can be subjective. So, for example, these two images on either side of the picture of the sky are what I would call sky blue. But you can see that they're not quite the same shade of sky blue. They are a little bit distinct. And if you were to Google the word sky blue, you're going to get a whole host of different shades of what might be sky blue. So the problem is it can be subjective, meaning from person to person, everyone might have a different version of sky blue. It's not a very clear referent. Even though it is a suitable referent in some cases, it's not going to, in every situation, clearly distinguish one object from another. Other kind of problems with it is that it is ambiguous, not necessarily a concrete, defined, definite descriptor is to use something like sky blue, and ultimately it can be circular. So we don't end up reaching the same conclusion. We end up going round and round trying to identify the exact descriptor sky blue. Some other examples you see here are lemon yellow. So if we have a lemon, the color of the lemon is lemon yellow. It's specific, except for lemons can be different shades of lemon yellow, and so not for every person might have a different idea of what lemon yellow means. There are some ways to get around this. Everything we talked about before, the color, those are what we call qualitative properties. They're qualities. And then we have what we call quantitative properties, and these are things that can be measured. So normally when you think of quantitative, you think of numbers. Now, a measurement uses a quantitative referent, and so not using something like lemon yellow, sky blue, but using what we call units. Okay? There are 3 steps to making a measurement. One is to compare the referent unit to the property being described. So then you follow a procedure specifying how the comparison is done, counting how many standard units describe the property under consideration. So if you were to measure a piece of paper, you would take a ruler and you would hold the ruler up to where one side of the edge of the paper is at 0, and then you're going to look and see where the other edge of the paper ends, and where that number is, that tells you how long the paper is. And whether or not you're using inches or centimeters is another discussion. So what is essential to every measurement are 2 things: the number and what unit you're using. If I measure a piece of paper and I say this paper is 8.5 long, well, you don't know if that's 8.5 inches or 8.5 centimeters unless I specify that. So you use the unit to very clearly define the referent that was used in the measurement, and it's important to make sure you use the unit. Without the unit, the number is meaningless. And also without the number, the unit is meaningless. Unless I know the exact number, I won't be able to necessarily understand the quantitative measurement that you've made. So how do we make a measurement? Well, once we determine what we're actually measuring, whether it's weight, length, those 2 properties are probably the most common that you would measure of an object, especially they're the most obvious parts of our physical world is how big or how much. So in this case, we're going to measure the length of what looks like we'll just call this a granite block. Okay, so I'm going to obtain a ruler. I'm going to line the edge up of the object on 0, and then I'm going to determine how far down the object goes. Okay, so it seems like it ends right about here. Now, the only thing about this example is there are no units. So we're going to say that this is in units of centimeters. Okay, so I'm going to write that in just so we have a unit to use. So this is centimeters. Okay, so it seems to me it's at least 1 and less than 1.5. So the length of my object is somewhere between 1 and 1.5. Now this is, if I'm counting off, this is 1.1, 1.2, 1.3, and 1.4. So now I know that the length of my object is at least between 1.3 and 1.4. But now I need to understand, is it closer to 1.3 or is it closer to 1.4? And so looking at the red line I drew, it seems like it's a little bit on the other side of 1.4. So I can tell now that it's somewhere between 1.35 and 1.4. And this is where we're going to estimate the last digit, because we don't necessarily know, is it 1.35 or 1.4? We don't have a way of determining that second decimal place. Okay? The estimation introduces what's called uncertainty, meaning we don't know the exact length, but we're going to guess it, and we're going to do our best job at guessing it with the information we have. So I'm looking at this and I'm going to say it's probably a little bit more than on this side of 1.35. So I'm going to say the length of this is approximately 1.37 centimeters. Now you may have looked at it and said, well, I think that's 1.36 centimeters, and that's okay, because what we did was we estimated the uncertainty of that last digit. If we were to know the second digit definitively, there would have to be additional tick marks between the smaller black lines so that we could count off and know exactly what the digit was. But we don't have that, so we have to estimate it. And that's a lot of what science is when it comes to making measurements, is dealing with a certain amount of uncertainty. So now we're going to talk about the measurement systems. The first measurement system that we're going to talk about is called the English system. So originally, the English system was based on parts of the human body. So there are examples here. There's the digit, the span, the foot, the cubit, the yard, which is the tip of your nose to the tip of your finger, an inch, which is about the first index joint on your thumb, and then the hand. And this is how people measured things. Before we had a system that told us exactly how many inches are in a foot, how many centimeters are in a meter, we just used body parts because it's what you had. But the problem is that, one, everybody has a unique body. And so an inch on my thumb may not be an inch on your thumb. And a foot on my foot, we know is not a foot on everybody's foot because we have different sized shoes. And same thing with wingspan. We don't all have the wingspan of Michael Phelps, or else we'd all be really great Olympic swimmers. So different units are not systematically related to each other, and they're also not systematically related to a set length. We didn't have rulers, so we didn't know what an inch was. But by the 1300s, standardization of the measurements began to happen by various English kings. So I think Henry VIII was one of the first ones, and he did the yard. And so from the tip of your nose to the tip of your finger. But it wasn't until 1879 that the English system was actually defined in terms of the metric system, which is our second measurement system. So the metric system is also called the SI system. It's the one that is used most exclusively throughout the world and pretty much the only thing you'll see in science. The English system, which is inches, foot, yard, those are things that we use here in the United States that are not commonly seen in other countries. But we do have the metric system still here in the U.S. So the metric system was established in 1791. By 1960, there were 6 base units, and since then we've added a 7th one. And so here are the list of the 7 base units that you need to know. The meter, which measures length, and the symbol for that is lowercase m. We have mass, which is kilogram, kg. So the unit for grams is just g, but in this case, the base unit is kilogram. Time, which is measured in units of seconds. Electric current, which is amps, capital A. Temperature, which is in kelvins, so there's no degree sign here, so make sure we have degree Celsius, degree Fahrenheit. There is no degree sign in Kelvin, and it's capital K. The amount of substance, which is in units of mole, M-O-L-E, but the unit itself is M-O-L. And then light intensity, which is candela, which is CD. And then all of our other units that we have derive from these 7 base units. So any other unit in science comes from these 7, some combination of the 7 to get another unit. So now we're going to talk about metric prefixes, and then we're going to practice. So metric prefixes are a part of the metric system only. They are not used in the English system. And the metric prefix scale is really used to take really big numbers or really small numbers and bring them into a scale, a number that is feasible. So instead of saying I have 5,323,170 chickens, we could express that using the metric scale as 5.1 mega chickens, which doesn't make a whole lot of sense when we refer to something like chickens, because 5 million means very clearly that's a ton of chickens. But when we're in science, I'm not going to say that I measured out 5,170,523 grams. We're going to abbreviate that down to megagrams. So the way it works is that this right here where it says none, this is what's called the base unit, which is what we just talked about, those 7 base units. And then we're going to have these metric prefixes. We have tera, giga, mega, kilo, hecto, deca, deci, centi, milli, micro, nano, and pico. And the way this works is you basically hop. So these are a factor of 1,000, okay, between them. Then when we get down to these are factors of 10, the smaller ones. And we know that 10 times 10 times 10 equals 1,000. And if you're not sure, just type it in. 10 times 10 is 100. 100 times 10 is 1,000. So while the difference between these smaller lines is by a factor of 10, the difference between the bigger lines is still 1,000. Okay? So then you can hop between them. So if we have, let's see, I'm going to pick one that's not in the middle of everything. If I want to understand the relationship between the two. 1 kilo equals 1,000 of the base. And no matter what it is, if I have 1 kilometer, that's 1,000 meters. If I have 1 kilogram, that's 1,000 grams. And so all you do is you can swap out the unit and add whatever is being measured, whether it's moles, grams, seconds, length, amps, and we put the numbers in there. Now, once you start going the opposite direction, remember you have to move the decimal different places. So y'all may remember these types of charts where if you had 5 and you said, what's 5 plus 3? Well, you do 1, 2, 3, and we know that that's 8. But then if you went backwards on these scales, and you said 5 minus 3, well, now we know we have to go the opposite direction. 1, 2, 3. So that's how they teach math to very basic introductory level, is by hopping and going different directions. Now, when you are using these charts, it's going to change. So if I'm going for, and I want to know the relationship between the base unit and milli. So right here, this is going to be 1 base unit has 1,000 milli. So there's 1,000 millimeters in a meter, and there's 1,000 meters in a kilometer. So the relationship is always going to be 1,000 to 1 on these larger numbers, and then it's a factor of 10 in these smaller numbers. And so what we're going to do now is practice some of these first things we've talked about. And specifically, we're going to practice converting between the metric prefixes using a similar type scale like this.